Here's the solution to W6. W6, they give us a differential equation, and first off they ask us to generate a slope field for that differential equation. So again, to generate a slope field, you take the points that they have identified on the graph that they give you and go point by point, take the x and the y coordinate of, let's say, that point, plug in the x and the y, and get the slope out of that. Remember, dy dx is the slope. And when you do that, after you get the slope, you draw a little line segment through that point that has the same slope as what you calculated. Again, plus or minus some error in drawing. Just make sure if it's a negative slope, make sure it's negative. Make sure if one should be steeper than the other, that it's drawn steeper than the other. Try to do things about right, but you don't have to obsess over them. So after you do all of those points and compute the slopes using x, y coordinates at each of those points, this is the slope field that you generate. Notice there are some zero slopes. Wherever x is 0, the slope is 0. Wherever y is 0, the slope is undefined. So at this point, well, you notice they didn't ask us to make any slopes on the x-axis where y equals 0. If they did, we would have to make vertical slopes or something like that. Okay, so that's part A. Should be pretty easy. Part B, now they're saying, okay, they're naming a particular solution to the differential equation. Bear in mind, what a slope field does is it gives us the family of solution curves to this. So each one of these, if I could connect this, I don't know how much information I really have here, but let's say that looks like that could kind of go through those with appropriate slopes. That would be part of the solution curve to one of the functions that solves this differential equation. One of the functions that acts like this, that has a slope that's equal to this thing at every point that it goes through. Okay, so now they're giving us or naming a particular solution, and they give us an initial condition. F of 1 equals -1. So that's this point, F of 1, right there. That's the point that they give us. So write the equation of the line tangent to F at 1, -1. Well, what do you need to write the equation of a tangent line? Or what do you need to write the equation of any line? You need a point and a slope. They gave us the point. We need the slope. How do you find the slope? Well, again, you have the x and the y. You plug it into the differential equation. That gives you the slope. Let's see what answer they got. They got in point slope form, which is the way you'd want to do it, right there. Apparently the slope at 1, -1 is 2. All right, so now, that again should be not so bad. You get a point for going that far. But now we want to use the equation of the line to approximate f of 1.1. This is so easy, but it's confusing. So look, we don't know what f of 1.1 is. But if you look at this drawing, I've kind of drawn part of the solution curve that goes through 1, -1. And here's the line tangent to it. What they're asking us to do in approximating f of 1.1, well, f of 1.1 is that point right there. But I have no idea of knowing what that point is because I don't know the solution. I don't know what y is. I don't know what f that function is. The best I can do is find this point right here. What's that point? That's the point on the tangent line when x equals 1.1. Notice that 1.1, that x value, is pretty close to this x value of 1. That is, the tangent line doesn't have very much x distance, very much time, if you will, to stray from the function that it's tangent to. So here is the error that we're willing to put up with by using the line to approximate f of 1.1. All right, so how do you do this? Well, you just plug 1.1 in for x into the equation of your line, and you get 0.08. So this height right here, this y, is negative actually 0.8. I plug 1.1 into the equation of the line. Last question, last part of this question is your classic differential equation, solving a differential equation symbolically. We want to find this particular solution. In other words, we want to find the solution to this differential equation subject to that initial condition. So we're going to separate the variables, integrate, but don't forget to attach a plus c to one of the integrals. And then we need to use the initial condition to find that c. And then we need to solve for y. Remember, the thing that we're looking for is a function. It's y equals some function of x. That's what we're trying to find. That's the solution. So there's the differential equation. There it is separated. That is, all of the y and dy stuff is on one side and all the x and dx stuff is on the other, where dy and dx are factors of their respective sides. So that's now separated. What do I do once it's separated? We integrate both sides. Notice they look like they're just primed, ready to be integrated. Y dy, I know that integral. The integral of negative 2x dx, I know that integral too. And there they are. Notice, whoops, they attached the c to one side. You don't need it on both, but you need it on one side. We'll talk about the points in a second, but that's a big penalty if you forget that c. So what do we say? Separate, whoops, that's here. Separate, integrate, and then celebrate, but you can't celebrate without a c. So once I have this general solution, now I can use the initial condition. The initial condition, f of 1 equals 1. So there's an xy pair. X is 1, y is negative 1. So I plug those in for x and y, and I solve this for c, and I get c equals 3/2. So I plug 3/2 back in for c. X and y go back in instead of their numbers at that particular point. And what I'm going to do here now is solve this for y. I solve it for y, and I get y equals, well, since y is squared, and I take the square root, I have a plus or minus that I have to contend with. Why did they pick the negative? Because if I have y equals, it would have been nice if they wrote y equals the square root of this thing. Y equals the square root of that thing, plus or minus. There's no way I can have a negative y come out of this square root unless there's a negative in front of the square root. That's why I choose the negative branch. If they gave me an initial condition of f of something else equaled a positive y, then I would have to pick the positive branch of the square root function. But since y is negative in the point, the particular point that they give me, the negative branch of the square root has to happen. So after all of this, it's easy to lose sight of what you've just done. You've found a function right here. This function has this derivative. It really does. And it goes through this point. Notice, just down here as an aside, don't ever do this on the AP exam. Don't do anything extra. But I did happen to compute y of 1.1 just to see. And y of 1.1, this value right here, is just a little bit bigger. Remember, they're both negative. Is just a little bit bigger than negative 0.8, which was our approximation. So f of 1.1 is indeed just a hair bigger than the approximation that we used, that we got by using the tangent line. Okay, so keep in mind, and this is a big deal, these points. Look at this. If you don't have a constant of integration, you're only eligible for the first 2 points, the separate and the integrate. That's a big penalty. Don't forget the C. If you can't separate the variables, you get nothing for that whole part. And this is 5 points, which is quite a bit of points for one single part of a question. Okay, so if you meet a differential equation on the AP exam, make sure you separate, integrate, and celebrate. And remember, you can't celebrate without the C. Thanks.